Okay, so we just finished our physics Rorschach test where you took a look at this picture of the electric field produced by the dipole. You searched your subconscious and you figured out what it looks like to you, whatever's going to help you remember what it is. And remember, all we're looking at, though, is a map. If we put a positive test charge at any location here, the field line direction will show you the direction of the force on that positive test charge. And if instead it's in reality a negative test charge, it would feel a force in the opposite direction. That's all it really is showing. But this also helps us get to rule number 3 on our list of rules, and hopefully you left enough room in your notes, that all field lines start on a positive charge and end on a negative charge. This really goes along with rule number 1, but it's good to list it as a separate rule. Start on a positive, end on a negative. This can be shown very clearly in the pictures we just showed. Start on positive, end on negative. Start on positive, end on negative. Start on positive, end on negative, somewhere over here. They're actually shown in these pictures as well. It's just that maybe it's not on the confines here, right? So all these field lines are starting on a positive. They're ending on a negative, just somewhere that's not in this picture. All these field lines here are ending on this negative. Where do they start on the positive? Just somewhere that's not in the picture. Although, can you see, if I take this picture and put them next to each other and connect the field lines and sort of smooth them out, I get this picture over here, right? This is this principle of what we call superposition, that really this is the superimposed field of these two ones put together and just sort of smoothing out the shapes. Okay, let's take a look at another complicated situation. Here we have 2 point charges equal and same. So this is on the second page of your notes page. We're going to make them both positive. So it's positive Q and positive Q. And we're going to give you some time to draw what you think the field looks like. Although before we do that, we have to list one more rule. And the rule here is rule number 4. The lines never cross. Remember, we're superimposing the fields of the two individual charges on top of each other and then thinking about the vector sum of them. And so the map, the end result, is really just the unique direction of the field at that location. So I want you to take some time, pause the video, go through the rules we've just been doing, thinking about superimposing the field from one charge on the field from the other charge, fill up the space, make sure you're using pencil because it's guaranteed you're going to do something wrong. That's okay, everyone does. And then come back and I'll lead you through it. In class, what I usually notice after giving that advice is that students start by looking at the original field we had done, the positive source charge. And so if we're all the way on the left-hand side, far away from the right-hand charge, we know the field's going to look pretty much undisturbed, and so it's going to have field lines pointing away. Hopefully you did something like that. And if we're all the way on the right-hand side, we sort of neglect the effects of the left-hand charge, the field lines are going to be pointing away. This is a really good start. Now at this point, I again want to just sort of pause what we're thinking about and make sure we understand. Are we drawing what these two charges do to each other? No, we are not. If I were to take these two charges and let them go, what would they do to each other? They would repel. And so I understand the confusion. These look like what these charges do to each other, but that's not what we're showing at all. Okay, in fact, remember, we're not even letting them go. This is electrostatics. We're fixing them in place. So what are we showing? We're showing what they would do to a positive test charge. If I put a positive test charge over on the left-hand side, it would be repelled by that positive charge more than the other one because it's closer. If I put a positive test charge over here, what would happen to be repelled by this one because it's closer to this one, even though it's also repelled by this one. It doesn't matter, right? It doesn't matter. Okay, so that's what all we're showing is the net effect on a positive test charge. So now let's look at the middle region. That's where it gets more interesting. If we put our positive test charge right here in the middle, and again, don't draw it, just imagine it there, what would happen? Well, from the charge on the left, it would feel a repulsion. From the charge on the right, it would feel a repulsion. What's going to happen in the middle? Well, these two fields will cancel. So the net field in the center is 0. But we just said by our rule, lines can't cross. So even though if you had drawn these field lines and stopped drawing them, the arrow indicates they keep going, they would eventually cross. You've got to get rid of them. So if you draw anything right here in the middle, erase it immediately. The field at the center is 0, so you can't even have a field line that would eventually go to the center. So get rid of it. If you have it, it's wrong. You must erase it. Now let's look at a more interesting position, right in the middle, but displaced vertically upward. And here we'll play our same game. What if we have just one charge to the other? So if we have just the charge on the left, which way would our test charge feel a force? It would be up and to the right, repelled away. What if we have just the charge on the right? It would feel a force up and to the left, repelled away. But they're both there, so again, we're not drawing any of this, we're just imagining it. Now we see that the horizontal parts of these forces, or fields, would cancel. Overall, they're pointing upwards, and so the net field right at that location points upwards. Now, we could do the whole game, more left, more right, but in general, the idea is we want to sort of draw the picture of the field produced by just this charge, and then alter it so it gets to that location, it gets the same direction we just described at that location. And this is where the idea of the field lines can't cross. And so we would draw a line that points away from the positive and then has to curve so that once it gets there, it points up. By the same token, we draw it over here, curving, so when it gets there, it points up, and now the field lines are not crossing. But they're definitely pointing away from both positive charges. All right, by symmetry, what if I put our positive test charge over here? Well, hopefully you recognize it's the same general idea, just pointing the other way. Right, so we just sort of replicate that, but now we feel a force downwards. And then we can sort of fill in some lines in between, some more curved lines. Really, all these lines should be curved a little bit. And so here's the net field produced by 2 point charges, equal and same when they're both positive. We have this sort of curved diamond shape. And if you want to fill in more over here, it's fine. You can draw maybe another line over here that arcs, and here that arcs, just that's getting a little bit, clustered over there. The point is, though, any field line that starts going this way just certainly can't cross through the middle, because the field is exactly 0 right there in the middle. Okay, here we have 2 point charges equal and same. I want you to fill in they're both negative, and I want you to, using your pencil, draw the net field produced by both of these. Again, make sure we're following all the rules we've established so far, and we're not reinventing the wheel. By the way, one last hint, in case you're still listening, I haven't paused it yet. The title of this picture is a huge clue. Okay, so yes, it's a fun game to imagine the test charge, all different locations, do that, but I just gave you this huge clue, the title of the picture, and so some of you probably drew it really, really quickly and drew it immediately. Because if this is the same title as this one, the shape should be exactly the same. Because on your notes page, it doesn't say they're both positive, both negative, it just has the title. The title tells you that the shape for this picture should be the same as the shape for this picture, but we do have all the source charges being negative, so what do we change? All the field lines point inwards towards them, because a positive charge would feel a force inwards towards the negative source charge. In fact, look at this. Here's a dipole. Here's positive, here's negative. You can't really see it on your picture, but mine you can. If I just connect this, and smooth out the field lines, we would get the picture of the dipole. So again, we're looking for all these connections. Okay, let's go back to our list of rules, and we'll do our last rule here. The density of the lines, or how close together they are, indicates the strength of the field. This is a very qualitative sort of thing, saying that if the lines are drawn close together on the picture, that's a stronger field. If they're drawn farther apart, that is a weaker field. And we can see it right here in these pictures. When we're close in by the positive charge, either one, the field lines are sort of close together. The farther away we get, the more the field lines spread apart. Same thing happens over here. The other pictures, like in the dipole, when we're close by the positive charge, we have a clustering of field lines. That's a strong field over here as well. In the middle, strong. Over here, though, there's very few lines per area, so it's a weaker field. And this rule is a very qualitative way of just showing that if you have a picture of the map of the electric field lines, you can tell it's strong over here, weak over here, strong over here, weak over here. Here, oh, we have double the field lines because it's double the strength of the field. So in this region, it's double the strength of the field because we have double the number of field lines, as opposed to this one over here. So this rule is a very qualitative one, letting you know the relative strength of the field at different locations in this map.